This is a secure programming presentation, but it's not intended to be complete. In fact, there's no possible way I could expound a complete secure programming, defensive programming, secure software engineering doctrine in 30 minutes. Instead, I want to just do a series of case studies of security issues I personally have encountered in programs I worked on. And the main takeaway I want you to get from my presentation today is not the specific outcomes of the case studies that I'm showing you, but more to encourage you, if you are a developer or if you're working with developers, to go beyond what is the security bug, what is the fix, and actually look at the contributing factors and the underlying causes and work out a doctrine to address those. So let's start with the Dogtag PKI, which is a lovely 20-year-old enterprise Java beast, which is just so much fun. And it's one of the main projects I work on. Like all big enterprise systems, it has an access control regime using access control lists. This is an ACL for Dogtag. The anatomy shouldn't really be surprising to anyone who's ever seen an ACL before. So basically, there's just a resource, a series of operations that can be performed against that resource that this ACL governs. And then, in this case, 3, but a number of access control rules that basically say, we're going to allow or deny these operations against this resource to accounts or tokens that satisfy these predicates. So in this case, anybody can list or read the authorities in the instance. Administrators can create, modify and delete, but Mallory, whether she's an administrator or not, may or may not be able to create, modify, delete the authorities, depending on this configuration, the evaluation order. So if you've seen Apache access control configuration, you will have seen something exactly like this. Basically, it's just a global configuration that says, do we process the deny rules first or the allow rules first? Okay, so that's the setting. Here's some code for processing the access control lists. It's simplified, but this is the basic idea. If the order is deny allow, we're going to grab the deny entries, we're going to run over those entries, and if any of those entries match the user's authentication token, we're going to throw an exception saying permission denied. If the order was not deny allow, so if it's allow deny, then we do that for the allow entries. And by now, some of you have probably seen the bug already. The second step is to do the same thing, but for the second part. So if it's deny allow, then we get the allow entries and process them. And if it's allow deny, then we get the deny entries and process them. And in the second stage, instead of kicking you out, if the rule matches, we let you in. Okay, so who saw the bug?
Getting the allow method function when you still be looking for deny.
Yeah, exactly. So if the order is not deny allow, which is the default, if it's allow deny, you're going to grab the allow entries at this stage, but then if any of the allow entries match, we're going to kick you out or reject the operation. And similarly, in the second stage, if the order is allow deny, we're going to grab the deny entries, but then let you in if the deny entry matches. So is everyone following?
Yeah.
Yep, sweet. So does anyone know what is the phenomenon that leads to a bug like this? If you know it, just shout it out. I'll say it's Boolean blindness is what it's called. Anyone heard of that? So a Boolean value is just true or false. What does that mean? What does true mean? What does false mean? In this case, on this particular slide, in the if expression toward the bottom, you're running this evaluate subroutine and it returns a Boolean. What does that Boolean mean? What does true or false mean? In fact, it means that the rule matched the token, and that's all it means. But it was interpreted as the permission is denied. And exactly the same thing happened on the next slide, but it was misinterpreted as the operation is allowed. So this is Boolean blindness. It's a pretty common sort of bug. It can lead to security issues and many other kinds of failures in programs. So when you understand the underlying issue to be Boolean blindness, then you've got to go beyond fixing the actual bug and ask, how can we prevent these sorts of bugs from arising in the first place? Oh, there was a CVE assigned for this. Actually, we think the impact was very low. We think it's potentially catastrophic, but we think it's very unlikely anyone was actually impacted by it because all the rules have their sense reversed. The behaviour is going to be so busted, and if the allow rules are kicking you out, basically no one's going to be able to do anything. So we think it's very unlikely that anyone would have changed this configuration and not noticed that everything was busted and reverted it. So we don't know, and we don't think that anybody was actually affected by this, but nevertheless we couldn't be sure, so they filed a CVE for it. So the principle here is basically avoid Booleans. Use Booleans as little as possible, and instead use custom types to express different cases of the operation of your program. The corollary is that you need to use tools, programming languages that support lightweight, easy creation of custom types. So you can use enumeration types in these languages, Java, C#, and so on. Python has enums. They're strictly typed, so they don't compare equal with, with integers or Booleans. But of course, it's dynamically typed, so it's going to end up being a runtime error rather than excluding a program at compile time. And on the bottom line, programming languages like Rust, Haskell, and so on let you go a lot further along these lines with full algebraic data types. So to fix this issue, basically we just introduce a bunch of enums to express different variables. So the ACL order is now an enum type, the ACL result is allowed or denied, and then we refactor the code. I'm not showing it all here, but we refactor the code, and instead of using Booleans to express the results of particular computations, we're going to use these enum types. So we no longer have the potential of Boolean blindness where a developer gets confused about what true means or what false means. The value actually says what it means. Okay, so that was case study one. The second one, FreeIPA, the other main program I work on, an identity management system. So it does LDAP, Kerberos, host-based access control, certificate authority, which happens to use Dogtag under the hood. When you're performing operations against the CA, the block diagram looks something like this. The user talks to FreeIPA with a Kerberos ticket to authenticate the user. FreeIPA, when it talks to the LDAP database, acquires a proxy ticket to operate with the same credentials as the user, so operating directly on behalf of the user. But when FreeIPA talks to the CA, for example, to issue or revoke a certificate, it uses what we call the RA agent certificate, which is a highly privileged credential that is able to do everything that any user talking to the FreeIPA framework might need to do. So this is a pretty major violation of privilege separation principles, and this led to some CVEs. So the first one, and it's live demo time. Yeah, well, I'll just do it and you'll see. So I'll just become admin, and I'm going to add a new user. So I'll add Alice. And I'm going to add Alice to a role called Certificate Auditors. So let me see if I can remember. Role add member, certificate auditors, user Alice. Okay. Okay, it's called certificate auditor. Okay, so Alice is now a member of the certificate auditor group. This group has permission to read and inspect certificates, but that's all. No other permissions to perform any kinds of certificate operations. I'll just become Alice now. And I'll do an IPA cert revoke 1, and that operation's going to succeed. Okay, non-existent certificate. Well, anyway, I just revoked. I don't even know what cert that is. Let's have a look. The point is, Alice should not be able to do this. Cert revoke. Oh, I actually revoked the audit signing certificate for the CA, but I could have revoked any certificate issued by this certificate authority. I thought revoking the CA cert itself, which is a self-signed CA in this instance, would have worked, but for some reason that didn't work. So, yeah. So this was quite a severe issue, actually. We don't know if it was ever exploited, but it's bad. So how could this issue have been prevented? Well, basically, we need to properly authorise operations in the FreeIPA framework. That's how you fix the issue. But the real underlying cause is this privilege separation violation. What we really ought to be doing is acquiring a credential representing the user directly, and using that to communicate between the FreeIPA framework and the Dogtag CA, and then enforcing these access controls in Dogtag. Retrofitting these changes or remediating, these architectural mistakes is a big effort. It's a big cost and it takes a long time. We're slowly getting there, but in the meantime, we just had to fix the bug by properly authorising it in the FreeIPA framework itself, as we do for all certificate operations. So that was good. So the principle here, never cut corners on privilege separation. Never, ever. Just, you have to do it right from the start. It will come back to bite you again and again. This one here was exactly the same sort of issue, but in this case they could actually delete sub-CAs that were created in the CA instance, or enable and disable them. And deleting the sub-CA also blew away the keys unless you back them up. So, yeah, that was a real hoot. Okay, so on to the next one. A bug in Firefox. Actually, I first discovered this bug in Python cryptography, but anyway, we'll get there. So, an object identifier. These are identifiers that appear in a bunch of protocols and formats. X509 certificates have them all over the place. LDAP uses OIDs extensively, SNMP, Kerberos. It's just pretty common in the crypto sphere as a way of identifying a thing, a concept. So this one here, 2543, that's the common name in a certificate subject distinguished name. Certificate extensions are also identified by OIDs. That just happens to be the one for the subject key identifier. Some of them are quite long. So an algorithm identifier, SHA-256 with RSA encryption, which is actually a signing algorithm, so go figure, but that's its OID. You don't need to know these OIDs, I'm just giving you an example of what they look like. That is also an OID. This one I found in a real certificate issued by an Active Directory certificate system when I was implementing some Active Directory integration in FreeIPA. And I went to add this certificate to FreeIPA as a CA, and I ended up getting a bug like this. So it ended up throwing a trace back and saying, oh, I can't decode the byte, we got an invalid start byte, or actually it was Python 2 at the time, so this is the one I saw, malformed OID. So read the OID, and then this wasn't the whole OID. It sort of stopped there, and sometimes when I ran it, that you got sort of a junk character, and I thought, okay, yeah. So everyone in the audience, maybe not everyone, most of you will have worked out that this was a buffer overrun. Whether it was an overwrite or an overread or whatever, I had to dig in and find out. So the actual bug was here. Python cryptography uses OpenSSL as its backend. It set the buffer length to 80, initializes the buffer, and then calls this obj to text, which is basically stringify an OID on the buffer, and then that was the return result. And then in a separate part of the code, it then tries to interpret that as an OID in Python cryptography's native types. And that would fail because it would overrun the end of the buffer and get some junk. And, well, you're lucky if you get some junk and it says, hey, that doesn't look like a number. You could crash or whatever. So the fix, obj to text actually returns the size of the buffer required to hold it. So you need to do a compare to say, is the return code greater than the length of the buffer that I allocated? If it is, we need to go again. We need to allocate a new buffer and call the method again. So that's how that one was fixed. There was also a bug in CPython, which was basically the same issue. They had a bigger buffer size, 256 by default, but the same issue existed. So yeah, why did this happen? Well, why they pick a buffer length of 80 in the first place? Well, yep, thanks OpenSSL man pages, a buffer length of 80 should be enough. Not so much. And this is quite bad. It's bad enough if you make a bad assumption in your own code. It's, I think, much worse if you propagate your own bad assumptions to other people, other projects, relying parties. So anyway, I hope I should send a pull request and fix the man page or something. This is an OID. I just made it up, but after I found these bugs, I thought, okay, let's go crazy. So I handcrafted a certificate with this OID in a certificate policy extension. And it ended up being, the stringification is 400 and high 400 something bytes or characters. So yeah, I just made this cert and started feeding it to different programs to see what would crash. Firefox crashed. Fun fact, you are right now seeing X11 forwarding used in anger. Okay, so this is an old version of Firefox. This was fixed in Firefox 55, which I think was nearly 2 years ago now. What do I want? Preferences. Yeah, so I'm going to security. Where is it? Advanced. Yeah, view certificates. Okay, so I'm going to try and import that certificate with the huge OID that I just showed you. So I'm going to go import. And let's view it, and bam, this just crashed, segfault. So there you go. That was a similar issue again. Firefox uses NSS, not OpenSSL. That was the CVE for this one. But the bug was basically the same thing. Filled up the buffer, didn't null terminate it because of a bad assumption about how big an OID can be. Yeah, the buffer size was 300. So I filed the issue and sent a patch, said, hey, you know, you've got a segmentation fault here. And then they're like, embargo it and all of that. And so it's like, I get it, I know, but I'm not a, you know. Yeah, exactly. And I just needed to fix the crash bug. I don't know how to exploit these kinds of bugs. I know that they can be. This one would probably be a little bit tricky because you'd have to convince someone to go and try and view the certificate in the certificate viewer. Firefox processed these certificates perfectly fine. You know, if it was a server certificate or something, there was no crash. So it was only when you tried to view the cert and get a pretty print that this bug occurred. Okay, so the underlying principle here, I mean, we need to stop relying on assumptions about input. I'm not saying you can't make assumptions about input. At the end of the day, you can't, say, oh, well, I'm just going to accept an OID of any possible length, like 1 gigabyte OID. It's just crazy. So you need to make assumptions sometimes, but you can't rely on those assumptions for security. So you need to validate and sanitize everything. And I really want to make the point that sanitization is not something that happens necessarily just once. It really depends on how you want to use the data. If you're going to print it to the terminal, you need to do one kind of sanitization to get rid of escape codes. If you're going to print data, use data as a file name, you need to perform a different kind of sanitization. So you can't ever declare data sanitized, really. You really need to be mindful of how you're using the data in each possible instance and do the right kind of sanitization and validation of the data for the use case. We also need to stop using C and start using memory-safe languages. Again, memory safety there's lots of different kinds of memory safety. This is not the talk for me to elaborate that, but basically we need to accept that the tools have gotten a lot better. Some people still legitimately do need to write their programs in C, but I do despair when I see new programs, user-land things, being started in very recent times, and people are just defaulting to C. Now, I think that's a bad practice. So, my security doctrine is don't do that unless you've got a very good reason, and certainly I encourage other people to use memory-safe languages. If you can't handle garbage collector, if your use case doesn't tolerate GC pauses, well, look at something like Rust, which can get you a lot further than C in terms of having confidence that you're not accessing out of bounds and that you're not leaking memory and so on. Okay, so the final case study is an unnamed online service at a company I worked on at a company before when I was at Red Hat. And it was just a web service for a particular industry. What do we got there? Okay, I'll tell you the story first. So my team lead was giving a live demo webcast sort of thing of the service to some customers to show them, how did the new features work or something like that. So he's talking to the customer or customers and says, okay, well, I'm just going to obviously have to start by logging in. And he typed the wrong password and he said, I've typed the wrong password. And then it let him in. And he said, I guess that was the right password. And right after the demo, he came to me and said, Fraser, we've got a problem. And it took me about 30 seconds to confirm, maybe not even that. I said, yeah, that's a problem. Okay, so what happened? The service was not written in Python, but this is just pseudocode to demonstrate what occurred. So the framework used an authentication library. The authenticate routine took the user name and the password, same as what most of them do, talks to the database, works out if everything, does the user exist, does the password match? Okay, if we're all good, we'll return true. If we're not all good, we'll raise an authentication error exception. And the application code takes the user and the password from the request environment, invokes this authenticate subroutine, catches the authentication error, or if it catches the auth error, it'll respond 401. Otherwise, the user is logged in, we'll go and do the thing. And then there was an update to the authentication library and it didn't throw an exception anymore, it returned false. And we're not handling that case in the application code. So there's no more authentication error, we just assume everything's good. And that was the bug, that's what happened. So if you look at the underlying causes, what I learned from this experience is there's a fundamental problem with exceptions in most programming languages, and that is that they're not actually part of the type signature contract of the routine, of the function. So you can change the exceptions that are thrown without forcing the application code using those routines to respond in some way. That caused this security issue. I'm sure it's caused other bugs in many programs. Well, it's definitely caused bugs in programs I've worked on. This is the only time I'm aware that it caused a security issue. But what I learned from this and what I've adopted as a part of my security doctrine is to avoid using exceptions if you possibly can. The corollary is that the return type shall express the failure cases of the function, which means that we need to be using tools that actually allow us to express these concepts and to ensure that the calling code handles the failure cases. I know what you're thinking, oh, return code checking, that just sounds horrible, and it is, but in modern programming languages we have nice abstractions to actually make it not unpleasant. Rust does a pretty good fist of this. So in Rust we have this result type. It's an abstract or an algebraic data type defined over two types. So you have a OK case, which returns a value of type T, whatever T is, and an error case, which returns a value of type E, whatever E is. It has a numeration type, so, well, this is actually another algebraic data type, but we can have an error type, express all the different kinds of errors that can occur within our program or within this library. And then the authenticate function, the function signature, the two parameters are user and password, as you'd expect, and it has a return type of result string error. The left-hand type variable is for the success case. So if it's successful, we'll return the username. We'll just say, this is the user that successfully logged in. If the authentication fails, then we'll return the error case with an auth error. And Rust ensures that the calling code handles both of these cases. So it's not possible to ignore the error case. Or it is possible, but you have to explicitly do it, which would not make much sense. So it's not possible to make this an oversight. Okay, so I'm nearly out of time and I'm nearly out of slides. So what have we talked about today? Well, I've shown you some case studies of security bugs that I encountered, either discovered or fixed them, and I expounded some of my personal security doctrine that I've developed as a result of thinking about these bugs and trying to work out what the underlying causes were and how can we reduce the risk of similar bugs occurring in the future. I really want to make the point that this is my security doctrine, and I want to encourage everyone to do the same process and to develop your own security doctrine based on your investigations of bugs that you've encountered, and of course to share your results, because if we don't talk about it and share the results, then the overall benefit to the industry is diminished greatly. And when I say doctrine, it has to be informed by evidence, and you have to be open to changing it as well in the face of new evidence or when learning about other people's results. Right? We want doctrine, not dogma, in security. So the principles that I expounded were to avoid booleans and use custom types, and therefore tools that let you do that. To never ever cut corners on privilege separation, more of a sort of software architectural concern rather than the nitty-gritty of programming. Don't rely on assumptions about input. You can make assumptions, but you have to validate and sanitize your data according to how you intend to use the data. Use memory-safe languages and avoid using exceptions, express failure cases in the result types of functions. The overriding principle, of course, is to learn from your mistakes, go beyond fixing the bug, and look at the underlying causes, develop a security doctrine, share your results. And I might also say to this crowd, if you've observed a contempt culture for developers, because we write the bugs, but ultimately we need to cease excoriating and focus on educating developers so that we work well together, and so that there's no resent between the two groups. And that's all I wanted to say.
Well, all right. It's funny when you mentioned that password bug. One of my favourites is Adam Boileau on a red team. I think he mashed the keyboard for a super micro, like KVM controller or something that was password protected. He just mashed the keyboard because he was like, shit, it's password protected. Mash, mash, mash. It dropped him into it. It bypassed the auth. That was a pretty good one.
Wasn't there an Apple bug similar to that recently? Like if you just had too many password failure attempts, it just let you in after that?
Yeah, okay, whatever. You're trying hard, it's fine. I don't know, I like the ones where they keep revealing the password when you go into like disk imager or whatever, and you could actually reveal the root password. But it seems like, the TLDR here, they're oldies but goodies, which is, don't trust unsanitized input and try to avoid C like the plague.
Yeah, I mean, I work at Red Hat, so we've got kernel developers and people, and also people maintaining old programs written in C. So it's like, it's not reasonable to call out those people for using C, given the context. But yeah, if you're starting a new program, you better have a darn good reason why you want to use C or other unsafe languages.
So we've got some questions for Fraser. We've got one right here.
In one of your use cases, you called out that the external library changed its failure response, and then that was what led to the authentication bug. In something that's as critical as sort of an authentication mechanism, where do you draw the line between using an external library or internalising that so that such updates don't bother your code?
So just repeat the question. I'll just repeat the question, which is, that authentication bug there really relied on a third-party library, some changes in that. So, how do you handle that? At what point do you start relying, for things like authentication, at what point do you sort of stop relying on outside libraries?
I believe that we should not be doing authentication ourselves. It should be factored out to libraries. Now, whether you have one library sort of at your organisation and all of the projects at your organisation use that, or whether it's third party, is a different question. The problem was that the library was actually correct. There was no bug in the library. It was rather that a contract change or an API change didn't force a response from the using program. So.
It was more a change that exposed the bug, I guess you'd say?
Well, yes. I mean, even was it a bug? Was it a bug in the application code? I would say no, it actually was correct, but the API change didn't force a response from the application code. And this can happen whether your authentication library is in-house or not. If you're using third-party libraries, continue to pull from the upstream and
use the ones they maintain.
Exactly, because there's a very high risk, and this is what happens. That once you've plonked it in your code base, if it's not what you're hacking on day in day out, you're not necessarily going to notice that there were issues, even if they were fixed upstream and downstream those patches.
I'd also say if you're going to change your API, change the name of the function.
It's not a bad idea.
Yeah, I mean. I think that's a way to mitigate the issue. I think that, it's a mitigation, it's a valid mitigation, but really we need to move to better tools where,
Well, I don't believe it's pseudocode either, because surely they defined that exception and it should have gone away, unless they were still using the exception for something else, in which case they're just bad programs.
Right, well, maybe the exception was used for something else. Now, I will say Java checked exceptions also mitigate this somewhat, because in application code, if you're catching an exception that is no longer thrown by the library code, that'll be a compile error. So it's another mitigation that a lot of people hate checked exceptions. I think they're actually a pretty good idea for Java.
All right, everybody give it up for Fraser Tweedale.